Hello, everybody. My name is Maksym Diachenko. I'm a CEO of XOresearch company, which mostly make medical products using the AI. But today's talk will be dedicated to the creation of AI for games in a bit unusual way. We will make it by learn itself, rather giving the rules, rather than create it using conventional programming. So, of course, I can't give you a ready-to-use recipe to create those because it's a pretty complicated area. But it depends on what is your game about. But what can I give you today is a kind of understanding what tools can you use to build the game AI in this way. So main idea is to get rid the manual phase in AI creation. So it's pretty obvious. And it allows us to build the AI with some interesting properties, like human-like behavior, while still maintaining some control over its creation. So talk will evolve around two parts of AI learning. One is the unsupervised learning, and another one is supervised learning on big data, where AI teaches by observing what people do. First, the most important part of this talk is the reinforcement learning, and it's kind of self-learning AI. Okay? Second part of the talk discusses this big data approach, and as I already mentioned, we believe you can make a human-like AI easily just by observing the data. Few words about me. Company name is XOresearch, as you can see. I'm a CEO and founder, and it was founded like 4 years ago, like an AI startup. Personally, I have a bit of experience as a game developer, as a developer, and at the moment I'm mostly doing artificial intelligence stuff, deep learning, and all those kinds of interesting activities that goes around AI and presenting to you today. Company specializes on weak AIs. By being weak, it means that it's not sentient, right? So it learns from a big data to perform some task, but it performs it really, really well because there's a lot of data to learn from. Our solutions include model, which converts free speech into machine-readable templates. It's pretty cool technology. It's currently in development, but actually it will allow you to get some free speech and to convert it to some template. And another pretty interesting tech is automated interpretation of electrocardiogram data, which detects a full range of possible heart pathologies and enables solutions for automatic 24/7 monitoring of people with heart diseases. And it's pretty important stuff because about 60% of this will be associated with heart diseases and everything that is heart-related in just short amount of time, like maybe 5–10 years. Okay, enough of ads. Self-learning AI. Let's talk about some advantages. First of all, you can get your AI up and running right after the first iteration of your game. Just right after the first iteration. Designers are not restricted in any way. They can model complex interactions between game entities and let the AI define meaningful actions on top of the list of what is possible within the game. Okay? Another advantage is that it's pretty easy to keep up with change in the game when designers change it. You just rerun the learning process and enjoy a new version. Easy like that. Also, this allows designer to quickly iterate on game rules, see what works, what doesn't work, just by looking what actions AI take and which not. And designers even can affect the AI behavior just by adjusting the rewarding function. I'll talk about this later. AI, yes, you can really learn from scratch every time, but we have some knowledge transferring techniques that can adapt existing AI to a new set of rules instead of relearning. And it's pretty handy. This would speed up the releases of new AI versions. And then through the AI with the data from human players, from like on first iterations, it may be designers or QA guys, and enjoy your AI learning from this data. We can even force it to mimic the mistakes and successes of those plays for some believable human-like behavior. And it's pretty easy, actually. And another interesting usage is to use it as a QA agent. So you can use your learned AI to test for game bugs, which is obvious. But in difference from classic unit testing approaches you're using for your games, it's not reliable in terms of coverage because it uses the most effective way to play the game. But it can generate a very surprising sequences of actions because it's AI. But nothing actually prevents us from learning the special version of this agent who would be motivated to use all the actions available to it, just like your QA guy is doing. Okay? And another consequence of using the big data for learning is the ability to decide, you can decide what data to show it. And yes, in this way, you can artificially limit its performance. Obvious usage for this is to create difficulty levels, because part of your game might not be understood by newbie players, and they should be given a chance to compete against the AI. Imagine usage of town portal scrolls in mobile games. It's really important to have them, but newbie players don't understand them. So when you train with such restrictions, your model delivers better experience to newbie players for all levels. There's another approach to the problem of difficulty levels. We call this adaptable AI. You create those by limiting or corrupting the data you provide to the model. In real time, of course, based on the performance of the player. By doing so, you can make it harder for your model to make the optimal choices and let the player beat it. Let us see what already done in the area of reinforcement learning. A bit high-level overview how it works. It's pretty easy. Basically, agent just performs some actions at each time step from the range of possible actions. Nothing else. It just presses the buttons or maybe giving some signals. It's a right arrow. And those actions, they change the environment, which streams its new state and some kind of reward to the agent back. It's the left arrows. So agent should decide on each time step what will work best given the circumstances. Environment responds with the next reward, some new state, and we continue like this. Pretty easy. And this simple idea and recent progress in deep learning allowed Google DeepMind team to make some really cool stuff. They learned their model to play 49 Atari games on a professional level just by looking at pixels. There was just pixels for a model and some reward. No game data, no prior knowledge for possible strategies, just a list of possible actions. They pressed the keys on the keyboard, and only a score as a reward function. Let me show something they published. Here's the model, plays Atari Breakout. Probably you recall this game. So at the moment, it just tries different actions, moving left to right, and see what's going on. It's the beginning of training. Not much success. Actually, I remember my first tries on this game. But after 2 hours of training, it starts to play like an expert, which is nice, considering it just plays with the environment by itself. Nobody guides it, nothing. It plays like a good player. But this is not the most interesting part. The most interesting part is after 4 hours of training, model realizes that digging through the wall to the left or right is the most effective technique to beat this game. Some of you who played this game knew this is pretty easy strategy to beat the game. And they did this for dozens of Atari games, and it worked really well. 49 was on professional level, better than humans. And you can find the list on the internet if you're curious. And there's coming a much more difficult case. Have you seen a game Go? It's you can see the board on the screen. This game is hard for the AI creating community because it has so many possible combinations that there's no way you can compute even a tiny part of them to use a brute force solution to win the game like they did with the chess. So the best AI so far played a bit above mid-level, and it used a whole bunch of handcrafted features created by people. It wasn't even near of any professional player, and it can't compete with them. But DeepMind team didn't use any of those handcrafted features except for basic rules and one single novice trick for AI. Instead, they built their architecture around deep learning with fascinating results. Their AI managed to win against world champion 4-1 in 5 series games. So it won 4 games, one were lost, which was unthinkable just a few years ago. And I should note, commenters of the match was a bit lost while trying to figure out which strategy AlphaGo is using. But those strange moves, they called it strange, were perfectly in line with the final strategy that led the model to win. Does it look like a creativity for you? So, how they did it? Pretty easy. Actually, they trained the model on large database of human moves. And database contained about 160,000 of games of 6 to 9 done human players with about 30 million moves in total. Not 30 million full games, but just moves. Okay? And what they found, that learned network managed to predict the human moves with the accuracy of 57% of cases. So it managed to understand the logic behind human moves in more than a half occasions. Pretty good stuff. And then they trained it further in an unsupervised way just by letting the model play a large number of games against other instances of itself while using the reinforcement learning to train. So it looks like a perfect strategy, right? Show some human performance and then let it discover and improve. Okay, so far so nice. let me summarize the basic architecture they used to play Atari games, as it influenced AlphaGo as well. DeepQ network first gets some experience through a mix of decided and random actions. It tries the game, basically. Then it reads the score to get the reward. Reward, of course, might use some other metrics beside the score. You may use any function. And this model used so-called replay memory. It is a memory of all actions and all outcomes of all games, of some games it played already. So this model used a lot of memory to learn. Then those replays were used to train the model itself, where it seeks to maximize the future reward considering some action in particular environment. So it plays, then learns itself. Then plays, then learns itself. Simple. And they repeated this simple cycle of playing and learning many times. This approach has some limitations, so. First of all, this architecture requires a lot of updates to propagate single successful action many steps back. In other words, if some good action led to high reward, good outcome, we need a lot of training, iterations to learn this. So the model trains slowly. Problem. Second, already mentioned problem, it's large memory requirements, so it used a lot of memory. You need a lot of memory to store replays. Easy, yeah? So this limiting this technique applicability. Third problem is a bit technical, but basically it says we cannot use all the instruments we have in reinforcement learning to learn this model. So no go yet. But to solve these issues, Google DeepMind team came up with another approach. They already published it not so long ago, a few months probably. It's called asynchronous deep reinforcement learning. It has some advantages comparing to previous approaches. First of all, it's cheap. It's so cheap that the team were able to train it on CPUs instead of GPUs as we used to. And there's no need to keep large replay memory, so it's memory efficient, really. Their algorithm basically does this. It spawns multiple instances of the same model, which use and update shared parameter set to learn it simultaneously. So many agents contribute to this model at the same time. And this speeds up the training radically. Because the network sees a lot of different situations in a short amount of time. And they propose some change to known agent architectures to get some improved results. I'll show this. So their model navigates Doom-like maze just by looking at pixels. So it should navigate and memorize it at the same time. So pretty cool. Yeah, just by looking at pixels. Fascinating stuff. Another example, they used this A3C agent to play Torque's game. Agent uses only directional buttons to control the car, and it looks at raw pixels. And the problem here is the car dynamics, which agent should predict to successfully control the car. It's pretty hard to do for human. Imagine how hard it should be for AI that just looks at the screen. Yeah, so some numbers for A3C agent for Atari Breakout game. We've seen it earlier. You can see the DeepQ network, blue line to the bottom, and 4 different types of agent they used. And you see the yellow line with A3C agents. You see how fast it learns. DeepQ network successfully trained learns much slowly. And so what I must say that we have a lot of progress in this area recently, and in near future will be. And here, the latest Doom competition where Facebook and Intel team won it. It's a full disc match. Bots are playing just by looking at pixels. Enjoy. Yeah, others can't touch him because they're playing bad. This agent was superior to them. So, how to use these techniques to build game AI? I'll give some high-level overview. So, define possible actions and restrictions for your entities. Let the developers define the agent structure, and it's a creative part. Gameplay programmers, meanwhile, should create the API for the agent to be able to query some analytical data, like can this tank reach this target, or what is the distance to some object, and so on. And then launch multiple instances of your agent and see them play and learn. Agent structure might use some kind of hierarchy, like strategic, tactical, and micro levels of Zoom. But the problem is that to make a decision, one single decision at some level, agent might require information from all of levels or different instances of itself. So it might be a good idea to, okay, so first of all, it could be a lot of data to process at each step, which can be, you know, just will disable your ability to build the AI because of this amount of data, because you need a very large networks with a lot of expression power to learn very complicated things. So it's better to split up. Yeah. So we have some text that will allow us to perform these tests. First, we need to somehow compress the data agent sees. Throw it with too much data, and it will learn slowly. And training will be even more slow if some events are rare in your data, okay, in your game. And we can use some pretty cool tech called autoencoders to handle this. A few slides on those coming next. Another possibility is actually downsample the data into something with much smaller resolution than the actual data, but then use technique called attention to focus on parts of the data in full resolution. So you're just processing small part of your data on each step, and instead of building one gigantic large agent, we could build a hierarchy of smaller compact models and let them communicate with each other freely. And motivation behind this split is coming from empirical observations in deep learning that the preferred way of increasing the so-called expression power, its capability of the model and capability of the model is to make the model taller with more layers instead of making it wider. So it's empirical. Okay, so autoencoder, simple idea. You can get your massive input, run it through the first network called encoder, and receive as the output some kind of latent representation of the input. We call this Z-code. It can be hundreds, even 1,000 times smaller than the input, depending on the nature of your data, of course. Then you push this Z-code through the decoder network, which should give you a fully reconstructed input. In this way, autoencoder learns just by simply observing your data, nothing else, any supervision. And the most intriguing part of those encoding and decoding networks that they might be used separately after they learned. For example, one might use encoder to compress the input and perform some classification on Z-code instead of full input. Because good point of doing this is that you can split the actual autoencoding and training of the classifier in time, because you might have a lot of data coming from well, we can actually, it's pretty technical. We should skip it. Yeah, we have another technique on top of it called variational autoencoder, and it's pretty successful model. I'll show you later how it works. But what we see here, that it compressed the digits. Data set is called NIST. Digits into just it compressed images of digits. Okay, so it's 784 pixels for each digit, and it compressed it only to two numbers, like XY. And then we visualize those numbers to the right. We just draw this space. And this slide shows that it has pretty nice property while collapsing the collapsing like 700 of pixels into just two numbers. And we have recurrent version of V that is capable of processing dynamic data. It's pretty important for dynamic. And a few words about attention mechanisms. So you have high-level overview, downsampled, then your attention mechanism select few areas it's interested in, and you can see them in full resolution. So this is how it works. It's pretty easy. Yes, you should select some finite amount of these attention zones for each time step, and in this way you make this viable. So about compact models, so you have one model for zoom level. Lower level iterates on entities, higher levels are used to operate on higher concepts, and they will do this automatically if you provide them with proper inputs. Just a bit creative, you should be a bit creative, but it's not that hard to split your data on levels. And you can augment these models with memory networks, and this will give them idea how to learn one shot, to learn from one single instance of something and then relearn it through the weights. It's a bit technical, but it's really important if you want to build this agent. And just let them freely communicate. And recent advances showed that it works really well when you split and communicate instead of building one gigantic model. And just train them end to end. Okay. A few words about controlling the AI. So you can adjust their work manually for design purposes, and you can corrupt the input. And it's pretty interesting tech because, see, if you're corrupting your input, you're limiting your model ability to do stuff efficiently, and you can hide some parts of data to learn it some important from design point of view, some important stuff. So corrupting might be a really good technique. Last part about the big data. So as I said, it's pretty easy. Stream the situations from players' computers, get it into kind of server, and let the AI learn from it. Easy. So difficulty levels are easy to create in this way because you can artificially limit your data by outcome, like good playing instances are put in. You can just divide it on bins, okay? And each bin corresponds to performance of the players and learn only from those bins. Okay, so you can do it right away. We have everything. We have GPUs, we have deep learning frameworks, and we have all those texts, and they are stable enough right now. So you can try right away. Just try it. It's not that complicated stuff. So, a few bonuses for you. First is the speech generation. Actually, if someone is interested, I might show after the talk how it works, because it's pretty cool stuff, and you can use text-to-speech to generate a lot of speech data that you should record if you're doing this in conventional way. So Google DeepMind, I should thank them for this talk. Their model, called WaveNet, is a high quality, and one single network produced a lot of different voices, and pretty cool stuff. And they have a faster version of it. I'm sorry about this temp, because we're already out of time. We have another tag. It's rephrasing tag. What it does, actually, it's like translation from language to the same language, just to get the rephrase of something. And it might be important for like when you're trying to populate large hub like city with characters, and you need them to say something, but you don't want to say the same thing each time. And the extra bonus, and it's pretty much controversial, if we can teach the AI to play Doom, why wouldn't we teach it to play Photoshop or Maya? Nothing prevents us. You might say that creativity is the limit, because you need some creativity to perform things. But I believe that creativity is the function, and it can be learned, as we seen with AlphaGo making some unexpected moves. And for you, it's a fixed costs, because you can reduce your costs of running a studio. And it's quite controllable. And I show why it might be controllable. In this video, you can see how guys just drawing stuff. Now they just drawing green lines, and this is grass for them. Okay? And it generates few pictures to the right, you see them. And then they draw some mountain, and pictures change. And then they drew the sky with the color they want it to be. And then they draw some white snow. And this runs on top of variational autoencoder we seen earlier. And while being bad quality at the moment, because they just trying the tech, but this is very promising. Thank you. Questions?
Thank you for your speech, first of all. So, my question regarding this last bonus you presented us. So, if we can avoid sculpting by human, right?
Yeah.
And
we're using
painting,
human as a tool at the moment.
Yep. So, you're in the one step to replace, for example, programmer or architect, right? So,
no,
artificial...
what I'm trying to say, that you can easily replace this handwork, okay? So you can replace this work of, you can just use text or voice or point and click to give the model the idea what you want to change. Like, please change these ears for something more rounded. I don't like elf's ears, okay?
Okay, I want to see new model of, for example, zombie, right?
Okay.
And it will implement it, recognizing my voice, right?
Yes.
So we can eliminate a lot of professionals, right? If we can deep learn the specific, right?
Yes.
What about, my question again, what about technical specializing? If we have some innovation in this area to replace the coding, I mean, right?
Yep.
Not architecting maybe, but coding itself.
coding itself should be replaced actually, because it's a pretty mechanical task, and you have no gains from doing it by hands. Because what you really want to do, you want to guide your development with intentions, not by just typing something or saying something. Maybe you can, I don't know. So yeah, you should look at this. This is the tool, not the replacement. But yeah, it will kill some jobs, probably most of them, in short amount of time. But I believe that in this way, people will be happier. They will not be forced to work somewhere just to keep up, just to paying their bills. Probably they will do some creative stuff, and probably they should be happier. And those who not, we will have probably robotic version of taxes, like 95%, 96%, and those money will be distributed to somebody who don't want to do anything. Why not, if we can? Any questions?
So you should afraid something to have. Have you seen the cartoon Wall-E 2008 by, as far as I can remember, Pixar?
Okay.
And they have artificial intelligence too. And in the near future, if this thing will be succeed with all that stuff, we will have something like this. And it isn't something we should have for. I think it would be a little bit dangerous for us, because we can lose our special feature as humans, and less our creativity, and less our exploration, and less everything that lead us to this point where we now. And artificial intelligence is such topic which must be very helpful.
I believe that we will not compete against AI, we will augment ourselves with AI. So actually, if you can somehow connect your brain, I mean your network of neurons, to some artificial network of neurons, actually you can intercommunicate.
Something like Deus Ex?
Yes, something like Deus Ex. And yeah, in this way we can augment ourselves by... So what I'm trying to say, that we can offload the tooling part on the AI and keep up the creative part. Because, of course, it's a pretty...
hard ethical question.
It's a pretty hard question, because actually nobody knows. Probably Elon Musk only knows. Yeah, he just created a company called OpenAI to build an AI that will be capable of beating other evil AIs.
I think it's a good business for us in future to avoid Terminators.
So creating evil AIs to, yeah, maybe.
You should definitely work on it. Mr. Doom, sounds like this.
We'll see. You never know.
I provided you a good business to do. Please present in future.
Yeah, I'll think about it. Anybody else?
Hey, while building the most sophisticated Go player is a noble cause, most games are dealing with AI that doesn't have to be the most sophisticated, but actually be a good match for the player.
Yes.
Right. I think there are two approaches for that. One is agents-based.
Okay.
Right? So having different agents, some of them will be smarter, the other will be dumber.
Mm-hmm.
And on the other side, you have stuff like Valve's AI Director, right, where there are no actual agents. Every entity is like this stupid thing that just follows orders. And then the director actually tells them what to do based on how the player approaches the game. So what do you think is a better approach, or if there is a better approach?
Sorry. Actually, it's all about learning, because to learn something, you need a model, and those presented today, like A3C agent, they already done. Yeah, you can just use them, read the paper, and create it. And at the moment, you don't even need to create any deep learning stuff, because it's already here. You can use TensorFlow, Cyano, Caffe, all this stuff. You have a lot of already published stuff. GitHub is full of it. You can find anything, any agent. A lot of people are posting them right now. So just use the search. Yes, and you can iterate on top of it. Okay, so you can get the performing agent that performs good for your types of game and iterate on top of it. Just use simple principles I've outlined. They're pretty simple. Yeah, that's it.
А можете чуть-чуть детальнее рассказать, как работает ваша система? Она принимает в качестве входных аргументов матрицу пикселей или что?
So the question is about how this model works. Actually, it's not a model. It's a complete vision of how those agents should be built, because it depends on your game. And you can't, at the moment at least, you can't build this, like build one agent and transfer it to the other game that is different. You may try and it may work, but idea is to that when your agents perform really well on top of pixels, if you provide them with structured data, they will perform much better. That's it. Because you see, learning the card dynamics from pixels, it's hard, but it's manageable for this model. Sorry.
Так у вас получается, нету API конкретно под игры заточенной. То есть у вас библиотека, которая, API для нейронных сетей.
We are AI creating company. We are not creating APIs at the moment. Sorry about that.
То есть у вас, грубо говоря, библиотека работает с нейронными сетями.
Yes, we are not doing APIs to use those AIs. Sorry. Thank you very much, everybody.